Welcome! Today's video is about clones. This is a very good re-entrance point to the lecture series Graph, Homomorphisms and Universal Algebra because the definition of clones does not rely on previous sessions. In the second part of the video I will link clones with material that we have seen earlier. Let B be a set. B stands for base set. We write O n sub B for the set of all operations on B of arity n. The set of all operations on B for all finite arities is denoted just by O sub B. An operation clone is a subset of O sub B which contains all the projections and is closed under composition. Our notation for the kth projection of arity n is pi sub k superscript n. The composition of an operation of arity n with operations g1 up to gn of arity m is the m-ary operation that you obtain by first applying each of the gi's to x1 up to xm and then applying f to the resulting n-tuple. By closed under composition I mean that if f and g1 up to gn are from C, then their composition must also be in C. One may think of operation clones as a generalization of the familiar concept of a permutation group. Permutation groups contain the identity, and they are closed under composition too. However, in clones, we have nothing that corresponds to the existence of inverses in permutation groups. Our prime example of a clone will be polymorphism clones. We better start by recalling the definition of polymorphisms, since actually so far we have defined them only for digraphs. However, the generalization to relational structures is completely straightforward. If B is a relational structure, an operation f over B of arity L is a polymorphism of B if it preserves each relation R of B, in the sense that if we apply f to tuples from R component-wise, we again obtain a tuple in R. We write Pol of B for the set of all polymorphisms of the structure B. Clearly, projections are polymorphisms, and polymorphisms are closed under composition. We have seen this already for digraphs, and it also holds for structures, by the same argument. Let's now reverse this. Instead of looking at operations that preserve some given relations, we start from a set of operations and look at the relations that are preserved by the given operations. Let F be such a set of operations over B. There are two natural definitions for F. The first definition is the clone generated by F, written by angle brackets around F. By definition, this is the smallest clone that contains F. So each operation in the clone, generated by F, can be written as a composition of operations in F and projections. The second definition is Inv of F. This is the set of all invariant relations. That is, the set of all relations on B that are preserved by every operation in F. Note that we may view Inv of F as a relational structure with domain B, whose relations are precisely the relations in Inv of F. Formally, this is not quite true, because for a relational structure you also have to fix a signature. But for what follows, the choice of the signature doesn't matter. This means that we may also consider Pol of Inv of F. This is the set of all operations that preserve all relations that are preserved by all operations in F. We already know that this set is a clone. Also note that clearly this set contains F. So it must contain angle brackets F. Interestingly, if B is finite, then we have equality here. It is not difficult to prove, and I leave it as an exercise. So let's draw the big picture. On the left, we will draw the set of all sets of relations on B. On the right, we will draw the set of all subsets of O sub B, ordered by inclusion. So the empty set is at the bottom and O sub B is at the top. On the left, I will order the sets by reverse inclusion. The reason is that I want to relate the two sets by Pol and by Inv. Pol takes sets of relations to sets of operations, and Inv takes sets of operations to sets of relations. These two operators form what is called a general Galois connection. This topic is not treated in the script, but one participant volunteered to make a video about Galois connections, so I'm looking forward to this. What we have just seen before is that if we start with a set of operations f, apply Inv, and then Pol, we obtain the clone generated by f. Angle bracket f is what is called a Galois closed set in this Galois connection. What happens if we start from a relational structure or a set of relations? First apply Pol and then Inv. The new set of relations certainly contains the set of relations we started with, but potentially it contains more relations. Which relations will be added? What do you think? Suppose you would like to know whether a certain relation is primitively positively definable in some graph, or more generally in some structure. For example, we would like to know whether the edge relation of T3, the transitive tournament with 3 vertices, is primitively positively definable in K3, the clique with 3 vertices. It is easy to see that this is impossible, because K3 has a non-trivial automorphism alpha. So everything that is primitively positively definable in K3 must also have this automorphism. This is nothing specific to primitive positive formulas, but would apply to any isomorphism invariant logic. Now let's look at the converse. Does the edge relation of K3 have a primitive positive definition in T3? If you look at this for a bit, you will realize that all primitive positive definitions fail badly. And this should also not surprise you, since the CSP of T3 can be solved in polynomial time, for example by the arc consistency procedure, whereas the CSP of K3's 3 colorability is NP hard. However, of course, we would like to have a proof without assuming that P is different from NP. Unfortunately, we cannot use the same argument as before. The graph T3 has no non-trivial automorphisms. So it seems that we need something stronger than automorphisms. And you might have guessed it already. Polymorphisms are just the right tool for this purpose. I will give a quick overview over the rest of today's video. We will start with the relatively easy observation that polymorphisms preserve all primitively positively definable relations. So in particular, Inv of Pol of a structure contains all those relations. Fascinatingly, this observation has a much more interesting converse. If a relation is preserved by all polymorphisms of a structure, then the relation is also primitively positively definable in the structure. This has some very interesting consequences for the constraint satisfaction problem. It means that the complexity of the constraint satisfaction problem of a structure is fully determined by the polymorphisms of that structure. Because if two structures have the same polymorphisms, then they primitively positively define each other. So their CSPs can be reduced in polynomial time to each other. And this brings us to the second part of the title of this lecture series, Universal Algebra. Instead of studying structures, we may study their polymorphism clones. And clones are one of the central topics of universal algebra. This is familiar to the fact that mathematical structures can be studied via their symmetries, via their automorphism groups. With the difference that polymorphism clones store much more information about a structure than the automorphism group.
We will now prove that polymorphisms preserve primitively positively definable relations. Again, B is our structure and F is a polymorphism. Let phi be a primitive positive formula with k free variables. So phi defines over B a relation R of arity k. We would like to prove that F preserves R. We have to show that if we apply F component-wise to k tuples in R, then the resulting k tuple is again in R. A k tuple A1 up to AK is in R if there are elements B1 up to Bn, such that for all I, the formula psi I, after replacing the variables y1 up to yk and x1 up to xk by a1 up to ak and b1 up to bn, is true in the structure B. If we now apply the operation F to the columns that you see in my diagram, we obtain elements that again satisfy psi I, because F is a polymorphism. This in turn proves that the k-tuple that we obtained from applying F coordinate-wise to the k-tuples in R satisfies phi, and hence is in R. End of proof.
The following theorem was discovered in the times of the Cold War, independently in the East and in the West around the same time. It says that preservation under polymorphisms is not only necessary, but also sufficient for primitive positive definability in finite structures. A relation is primitively positively definable in a finite structure B if and only if it is preserved by all polymorphisms of B. We write Pol of B for the set of all polymorphisms of B. And we have already proved the easy direction of the theorem. The proof of the interesting direction is actually again very short. Suppose that R is preserved by all polymorphisms, we have to come up with a primitive positive definition of R. We start by enumerating the tuples in R. Let M be the number of tuples in R. Then we enumerate the k-tuples in R with an index in the superscript. Now we consider the mth power of B. We enumerate the elements of the mth power in such a way that the first k tuples are exactly a11 up to a1m and ak1 up to akm. And this already gives us the primitive positive definition. B to the m is a structure, the mth power of B. Phi is the conjunctive query of B to the m, where all but the first k elements are existentially quantified. So this gives us a primitive positive formula with k free variables. Those of you who forgot what a conjunctive query of a structure is have to revisit the section about relational structures. It's explained there. Now, why does our formula phi define our relation R? The easy direction is that all tuples in R satisfy phi. Because if B1 up to Bk is a tuple in R, then it will be listed as A1i up to Aki for some I. But then the ith column in B to the m provides witnesses for the existentially quantified variables that show that B1 up to Bk satisfies phi. Alright, for the converse, suppose that B1 up to Bk satisfies phi in B. I claim that there is a polymorphism of B that maps A1i up to AMI to Bi. So the polymorphism has arity M. The reason is that every solution to phi is a homomorphism from B to the M to B, and therefore a polymorphism of B. The witnesses for the existentially quantified variables in phi provide the image points of this polymorphism. And since F, by assumption, preserves R, we conclude that B1 up to Bk is in R, and this finishes the proof.